James Webb Telescope often gets called the replacement for Hubble. After all, Webb is the scientific successor to Hubble. Its science goals were motivated by results from Hubble. Hubble's science pushed us to look to longer wavelengths to go beyond what Hubble has already done. In particular, more distant objects are more highly redshifted, and their light is pushed from the UV and optical into the near-infrared. Thus observations of these distant objects, like the first galaxies formed in the universe, for example, requires an infrared telescope. This is the other reason that Webb is not a replacement for Hubble. Its capabilities are not identical. Webb will primarily look at the universe in the infrared, while Hubble studies it primarily at optical and ultraviolet wavelengths, though it has some infrared capability. Webb also has a much bigger mirror than Hubble. This larger light collecting area means that Webb can peer farther back into time than Hubble is capable of doing. Hubble is in a very close orbit around the Earth, while Webb will be 1.5 million kilometers away at the second Lagrange, L2 point. This is comparison of the Carina Nebula in visible light, left, and infrared, right, both images by Hubble. In the infrared image, we can see more stars that weren't visible before. Webb will observe primarily in the infrared and will have 4 science instruments to capture images and spectra of astronomical objects. These instruments will provide wavelength coverage from 0.6 to 28 micrometers. The infrared part of the electromagnetic spectrum goes from about 0.75 microns to a few hundred microns. This means that Webb's instruments will work primarily in the infrared range of the electromagnetic spectrum, with some capability in the visible range, in particular in the red and up to the yellow part of the visible spectrum. The instruments on Hubble can observe a small portion of the infrared spectrum from 0.8 to 2.5 microns, but its primary capabilities are in the ultraviolet and visible parts of the spectrum from 0.1 to 0.8 microns. Why are infrared observations important to astronomy? Stars and planets that are just forming lie hidden behind cocoons of dust that absorb visible light. The same is true for the very center of our galaxy. However, infrared light emitted by these regions can penetrate this dusty shroud and reveal what is inside. Webb will have an approximately 6.5 meter diameter primary mirror, which would give it a significantly larger collecting area than the mirrors available on the current generation of space telescopes. Hubble's mirror is a much smaller 2.4 meters in diameter, giving Webb around 6.25 times more collecting area. As the Earth orbits the Sun, Webb will orbit with it but stay fixed in the same spot with relation to the Earth and the Sun, as shown in the diagram to the left. Actually, satellites orbit around the L2 point. As you can see in the diagram, they don't stay completely motionless at a fixed spot. How far will Webb see? Because of the time it takes light to travel, the farther away an object is, the farther back in time we are looking. This illustration compares various telescopes and how far back they are able to see. Essentially, Hubble can see the equivalent of toddler galaxies and Webb telescope will be able to see baby galaxies. One reason Webb will be able to see the first galaxies is because it is an infrared telescope. When we talk about the most distant objects, Einstein's general relativity actually comes into play. It tells us that the expansion of the universe means it is the space between objects that actually stretches, causing objects, galaxies, to move away from each other. Furthermore, any light in that space will also stretch, shifting that light's wavelength to longer wavelengths. This can make distant objects very dim or invisible at visible wavelengths of light, because that light reaches us as infrared light. Infrared telescopes, like Webb, are ideal for observing these early galaxies. What about Herschel? The Herschel Space Observatory was an infrared telescope built by the European Space Agency. It too orbited the L2 point, where Webb is. The primary difference between Webb and Herschel is wavelength range. Webb goes from 0.6 to 28.5 microns, Herschel went from 60 to 500 microns. Webb is also larger, with an approximately 6.5 meter mirror versus Herschel's 3.5 meters. The wavelength ranges were chosen by different science. Herschel looked for the extremes, the most actively star-forming galaxies, which emit most of their energy in the far infrared. Webb will find the first galaxies to form in the early universe, for which it needs extreme sensitivity in the near-infrared. While we now know of thousands of exoplanets, planets around other stars, the vast majority of our knowledge is indirect. That is, scientists have not actually taken many pictures of exoplanets, and because of the limits of current technology, we can only see these worlds as points of light. However, the number of exoplanets that have been directly imaged is growing over time. James Webb will open a new window on these exoplanets, observing them in wavelengths at which they have never been seen before and gaining new insights about their nature. Exoplanets are close to much brighter stars, so their light is generally overwhelmed by the light of the host stars. Astronomers usually find an exoplanet by inferring its presence based on the dimming of its host star's light as the planet passes in front of the star, an event called a transit. Sometimes a planet tugs on its star, causing the star to wobble slightly. In a few cases, scientists have captured pictures of exoplanets by using instruments called coronagraphs.
As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
These devices block the glare of the star in much the same way you might use your hand to block the light of the sun. However, finding exoplanets with this technique has proven to be very difficult. All that will change with the sensitivity of Webb. Its onboard coronagraphs will allow scientists to view exoplanets at infrared wavelengths they've never seen them in before. Webb's unique capabilities. Coronagraphs have something important in common with eclipses. During an eclipse, the moon blocks the light of the sun, allowing us to view stars that would normally be overwhelmed by the sun's glare. Astronomers took advantage of this during the 1919 eclipse, 100 years ago on May 29, in order to test Albert Einstein's theory of general relativity. Similarly, a coronagraph acts as an artificial eclipse to block the light from a star, allowing planets that would otherwise be lost in the star's glare to be seen. There is, no doubt, a population of planets that are fainter than that have higher contrast ratios, and are possibly farther out from their stars. With Webb, we will be able to see planets that are more like 10 million, or optimistically, 100 million times fainter. To observe their targets, the team will use high-contrast imaging, which discerns this large difference in brightness between the planet and the star. Webb will have the capability of observing its targets in the mid-infrared, which is invisible to the human eye, but with sensitivity that is vastly superior to any other observatory ever built. This means that Webb will be sensitive to a class of planet not yet detected. Specifically, Saturn-like planets at very wide orbital separations from their host star may be within reach of Webb. The James Webb Space Telescope will be the world's premier space science observatory. Webb will solve mysteries in our solar system, look beyond to distant worlds around other stars, and probe the mysterious structures and origins of our universe and our place in it. Webb will be able to peer even farther back into the origins of the universe, to 13.6 billion years ago, and perhaps even earlier. Astronomers hope that catching a glimpse of the first stars that ever formed will better our understanding of the cosmos. Astronomers hope Webb will finally allow them to see in high-resolution detail what's going on inside the dust clouds where stars and planets are being born, because unlike visible light, infrared wavelengths can penetrate that dust, revealing the galactic embers within.